Imagine you're reading a book. You start a sentence. Okay. But here's the catch. The moment your eyes hit the second word, the first word just, poof, it's erased from your memory completely. Totally gone. Then you read the third word, and the second word vanishes. You're basically trapped in this constant state of amnesia, seeing every single word in total isolation. That sounds awful. You wouldn't be able to understand anything. You'd sat and just, but you couldn't derive any meaning at all. But here's the crazy part. Up until, relatively recently, that's exactly how most neural networks worked. They had no sense of time, no sequence. They were stuck in that rolling amnesia. Yes. But today, we're talking about the moment AI sort of woke up and realized that time exists. We are talking about how we gave machines a memory. It's such a fundamental shift in deep learning, recurrent neural networks. And our mission for this deep dive is, I think, pretty clear. We need to understand how we went from the AI we talked about last time, these convolutional neural networks, which are amazing at looking at a static photo of a cat, read a snapshot in time, to an AI that can listen to a song or translate a speech or even write a poem. We're moving from space to time. That is the perfect way to frame it. I mean, think about our last deep dive on CNNs. Those they see an image all at once, right? The relationships are spatial. The dog is next to the tree. Right. But the world isn't a photograph. It's a movie. It flows. Yeah. And that flow is sequence. Okay, so before we get to the solution, these recurrent neural networks, let's just really unpack why the old stuff failed. Why couldn't a standard feedforward network just learn a language? Feedforward networks have, and I'm quoting here, no memory of previous data. Every single input is treated like it's the first thing the network has ever seen in its life. So if I say hello, it hears hello. If I say it again 5 seconds later, it has absolutely no idea you just said it. Zero context. But there's an even bigger sort of structural problem, which is standard networks need a fixed size input, a rigid box you have to cram your data into. Meaning if the network is built to handle, say, 10 numbers, you have to give it 10 numbers. No more, no less. Precisely. Now just think about language. How long is a sentence? Could be anything. Go is a sentence. Or it could be a whole paragraph from a novel. Exactly. So what do you do with the word go if your network demands 10 words? I guess you pad it out, fill the other 9 slots with nothing, just zeros. Right, you pad it. Or even worse, if you have a really long sentence, you have to just chop it off. It's so clunky. Yeah. Early attempts to get around this, like n-gram models. Oh yeah, n-grams. That's basically just looking at the last couple of words to predict the next one, right? Yeah, if you see peanut butter and booze, you're probably going to predict jelly. Yeah. But they have such a tiny window of context, they can't remember the subject of the paragraph from 3 sentences ago. They don't have what the source calls a hidden state. Okay, so let's bring in the hero of the hour, the recurrent neural network, or RNN. What's the big aha moment here? If I'm looking at a diagram, what's different? The loop. It is literally a loop. In a standard network, data flows one way. Input, hidden layers, output. Done. A one-way street. A one-way street. In RNN, the output of the hidden layer is actually fed back into itself. It becomes part of the input for the very next step. Whoa. So it's kind of talking to its future self. That is a fantastic way to think about it. As passing a little note to the next moment in time. And that note, the distributed hidden state. Okay, distributed hidden state. Let's break that down. It sounds a bit like jargon. It's just the network's memory. That's all it is. Yeah. So when the network reads the word cat, it's not just processing CAT, it's processing cat, plus the hidden state it just got from the previous word. Ah, so if the previous word was black, the network is now effectively processing the concept of black cat together. It's carrying the context forward. It's carrying baggage, but in this case the baggage is everything. And while the diagrams show this as a loop, they call it unfolding the network. Looks like they just take the loop and stretch it out into a long chain. Exactly. So don't think of one network looping. Think of a long line of clones. You have the network at 1.0 p.m. It does its thing, creates a memory, a hidden state, and passes it to an identical clone of itself at 1.01 p.m. It's a bucket brigade. They're passing the memory bucket down the timeline. That's it. And this unfolding idea is so important because it turns a problem about time back into a problem about space, which means we can use math we already know to train it. Okay, so now we have a machine that can handle sequences. A ton of applications. That was basically anything that unfolds over time. Voice, music, text, but also things like financial data or, scientific readings. Finance makes total sense. A stock price today, say $100, is meaningless on its own. You need the sequence. Was it $50 yesterday or $200? Makes all the difference. Yeah, context is everything. Speech recognition. That's a huge one. Taking audio waves and turning them into words. Think about the phrase ice cream versus ice cream. Acoustically, they're almost identical. They are. If you just took a static snapshot of that scream sound, you couldn't tell the difference. Right, you need the context. If the words before were I really love, the RNN predicts ice cream. If the words were that haunted housemaid, it predicts ice cream. The hidden state carries that food context or scary context, and it changes the prediction. And then there's machine translation, which is fascinating because the input and the output sequences can be different lengths. That always messes with my head. The English phrase I am hungry is 3 words. In French, it's je faim, 2 words. A rigid network would just break. It would completely break. But an RNN, it can read the entire English sentence first, and it packs all of that meaning into its final hidden state. Then it sort of switches gears and starts generating the French, 1 word at a time, unpacking that meaning. So it digests the idea first, then it speaks. That is so cool. There's one diagram that actually made me laugh. It's showing the network trying to predict the next word. It shows the word awesome going in. The prediction is sauce. Yes. Awesome leads to sauce. It's a funny example, but it shows a key function the lecture mentions, the Softmax function. The network isn't just yelling sauce, it's actually giving a probability to every single word in its vocabulary. Oh, so sauce might get a 40% chance, day might get 20%, and I don't know, zebra gets 0.001%. It's literally betting on what comes next. It's a prediction engine. Okay, so we've got the concept, the loop, the memory, but how does it learn? We've talked about backpropagation before, tweaking the knobs to reduce error. Does that still work here? It does, but with a pretty major twist. BPTT, backpropagation through time. It sounds like a movie title. It kind of feels like one. Remember that unfolded chain of network clones we talked about? Bucket Brigade? Yeah, so on the forward pass, you feed the sentence in, the clones pass the memory bucket down the line, and you get a final prediction. And if the prediction is wrong, then you have to send the error signal back. But not just one step back. You have to send it back through time, all the way to the beginning, building up a stack. Like a stack of pancakes, exactly. As you go forward in time, you're putting pancakes on the stack. To learn, you have to peel them off one by one, going backwards from the last word to the first. So you're tracing the blame. If it messed up the last word of a sentence, the mistake might have actually happened when it misunderstood the first word. Precisely. The error signal has to travel all the way back to the start to adjust the weights correctly. And this is where we meet the villain of our story. The conflict. I knew it was going too well. RNNs are hard to train. Why? The vanishing gradient problem. The keys of the vanishing gradient. What's vanishing? The error signal. The blame. See, to adjust the weights, you need a gradient and number that tells you how much to change them. But when you backpropagate through time, you're multiplying that number by the weights at every single step. Okay. And what happens if you take a number less than 1, say 0.5, and you keep multiplying that by itself? It gets smaller and smaller, 0.25, 0.125. Right, now imagine a sentence that's 20 words long. You're doing that multiplication 20 times. Yeah. By the end, the number is so tiny, it's basically 0. So the signal, it just vanishes. It evaporates into nothing. The network at the beginning of the sentence never gets the message that it made a mistake, so its weights don't update. It just stops learning from anything that happened in the distant past. Which means the RNN can learn short-term things like awesome sauce, but if it's a long, complex sentence, it fails. It can't learn what are called long-range dependencies. The pilot, who had flown planes for 20 years and loved the clear blue sky, suddenly crashed. The RNNs crashed. But by the time the error signal gets back to the beginning, it's so weak it has forgotten who the subject was. It might think the sky crashed. It becomes a goldfish again. That's a massive, massive problem. It is. Exploding gradients, which is the opposite problem. The numbers get huge and the whole thing crashes. But vanishing is the one that really held the field back for years. So how did we beat the villain? This is where the lecture shifts to a whole new architecture, right? The LSTM, the long short-term memory network, which is a bit of a confusing name, but I get the point. A memory that can be both short and long. It's the elegant solution to the vanishing gradient. LSTMs replace the simple neurons in an RNN with something more complex, memory block. And inside that block, you have a system of gates. I love this analogy. We're moving from a simple pipe to a whole plumbing system with valves. That's a perfect way to put it. 3 specific gates. An input gate, a forget gate, and an output gate. Okay, let's walk through them. I'm the input gate. What's my job? You're the bouncer at a club. You look at the new information coming in and you decide if it's important enough to let into the memory cell. A new character is introduced. You swing the gate wide open. Someone just says, you keep it shut. Got it. Okay, now I'm the forget gate. This feels deep. Why would a memory network want to forget? Because context changes. If a character dies in chapter 2, you need to forget that they're the subject of the sentence in chapter 5. The forget gate looks at what's already in memory and decides what's now irrelevant. It prunes the memory. It's the Marie Kondo of AI. Does this old piece of information spark joy? No, let's thank it and let it go. Exactly. And finally, the output gate. It decides when the information inside the memory cell is actually useful to the rest of the network for making a prediction right now. So these gates are like little managers for the memory, but how does this technically fix the vanishing gradient problem? This is the absolute key detail in the lecture. The memory cell itself has a direct linear connection to itself over time. Linear meaning a straight, uninterrupted line. Yes. In the old RNN, the signal got multiplied and squashed by functions at every step. In an LSTM, there is an express lane, a superhighway where the gradient can flow backward through time without being repeatedly diminished. So the error signal can get from word 20 all the way back to word 1 without evaporating. It preserves the signal. It allows the network to remember that the pilot was the one who crashed, even if there are dozens of words in between. That feels like a monumental breakthrough. It explains why LSTMs were the kings of translation and text for so long. But the notes mention a younger sibling, right? The GRU. The gated recurrent unit, yeah. It's described as a streamlined version of the LSTM. Better. Or just, cheaper. More efficient, really. An LSTM is pretty heavy, with 3 separate gates and 2 internal states. The GRU is simpler. It merges the memory cell and the hidden state, and it combines the input and forget gates into one single update gate. So it's doing more with less hardware, basically. Fewer parameters, which means it's faster to train. And in many cases, it performs just as well as the LSTM. It's the minimalist's recurrent network. So we've gone on this whole journey. To recap for you, we learned that old school AI was stuck in time, looking at static snapshots. RNNs gave AI a memory by creating a loop. But that memory was leaky. It vanished. So we had to invent these clever gates, LSTMs and GRUs, to manage that memory, creating a kind of information superhighway that lets AI finally understand sequence, context, and time. And that's the fundamental tech that powers the voice assistant on your phone, the translation app you use, and so much of the text generation we're seeing everywhere today.